So last time we solved this diffusion equation. So for the case of the Gaussian solution in an infinite surface in an infinite medium. So we have this dose q we approach this dose q as a delta function. Now this corresponds to the case of implant a very narrow peak of dopant at a particular depth. And now we will look at other cases. So the first case is the Gaussian solution near a surface. This corresponds to the case of the typical diffusion process. So for the typical diffusion process, so we have the dopant gas, so only the top layer here. This is the near the surface, the top layer gets doped. Then afterwards, so we have this drive in for the profile control. So if this is very thin, if the top layer here is very thin compared to the final thickness, then we can approximate this thin layer as the delta function. You can see here. So we have this initial profile we assume is like a delta function. And to solve this, so we have the diffusion only to the right side, only to the downward. To solve this problem, so we imagine we have another dose Q on the left side, and we can also diffuse along this side. This is called virtual diffusion, because you can see in this case the dopant cannot, there is no after diffusion. But here, so it is called a virtual diffusion. Then the total dose will be, we have a dose here and we have another dose here. So then the profile will become like this. Now this profile is the same as this one, except that there is no factor 2, this factor 2, because here we have 1Q, we have 2Q. So then this is the solution for this case. For this one, for the top surface, you can we set 0t x equal to 0, x equal to 0. So we have this one. So we have this profile. So this CS has nothing to do with the solid solubility. It just says this is just the dopant concentration near the surface, and it will decrease with time. For the junction depth, so we go back for the junction depth. So we have seen this slide. So we have this background. So we have this background doping. Background doping is NB. And then we have this doping. So this is the Gaussian. So we have this Gaussian profile. So the junction depth as given by the point is that this profile is the same as this background. So this is the junction depth. So this is xi. So now we'll come back. So we set this one equal to C background equal to CB. Then we can solve xj equal to this one. Then we can rearrange it. It become like this. So the concentration gradient is partial C over partial H given by this formula here, and the p-n junction xi for the gradient is given by this number. So now we look at another case. In this case, it is the area function solution for in an infinite medium. So this corresponds to the case, for example, putting a very thick, heavily doped epitaxial layer on a lightly doped wafer. So here we have something like this. So here we have the silicon. This one is lightly doped. Then we put a silicon with heavy doping. We have heavy doping here. You can see here. So we have the dopant here. On the left side, this is 0. So on the left side, this you can see, this is the top side. So on the top side, we have this heavy doping silicon. And on the right side, we have no doping. So now we want to show how will the top surface. This is the. So how will this dopant here will diffuse into the under layer? This is the. So here we assume this layer here is very thick. This one is very thick. So we have the even in the structure of the material, because it is very thick. We can assume it's given in the structure of material. So in the half plane can be considered to be made up of a sum of the Gaussians. So that is for all the dopant here we divided into many slices, So we divide into many slices like this. Then each of them have the dose C times delta x. So C delta x. So we can approach this one. We can approximate this one as the delta function. So as the delta function. Then then the total dose profile, the total profile will be the sum of all the xi values. So then we have this formula here. So we know so this one comes from here. So this is the profile with the factor 2 here, with the factor 2 here. So then the dose become C delta xi. Then we take the C out. So we have the delta xi still inside. Then we have this exponential part. So the sum can be approximated as the integration. So when the delta xi is very small, it becomes an integration. So we have this one. Then xi becomes the alpha. And now we define x minus alpha equal to 2 square root dt equal to eta. Then we have d alpha equal to minus 2 dt. So we have this one. So then we put this one into here. So we have here. So we have this one. So the range, the integration from minus infinity, when this is minus infinity, it becomes plus infinity. Eta equal plus infinity. Equal to 0, alpha equal to 0 corresponds, give you this one, give you this one. So then this one you can see is reversed. Top, bottom from here is reversed. But here we have a negative sign. We have negative sign here. Then so we have this one. E minus e squared dE. So this one from here to here is equal to from 0 to infinity minus 0 to this one. We know that we have seen e minus 0 to infinity. So we have done this integration last time. Square root of pi divided by 2. So this one equal to the square root of pi divided by 2. So we define this is called the error function. We define the error function as this one. So the range is to z. The z appears here. Then this one becomes 1 c over 2 1 minus error function at this value here. Then we define the complementary error function equal 1 minus error function. Then in the end, so this one becomes c over 2 complementary error function x over 2 square root dt. So this is the case for this diffusion from the top diffuse to the bottom. So now we look at the profile here. So with this one, we can draw it. So initially we have this green color here. This initial we have this top doping, bottom no doping. So for t equal to t0 become this one, for t0 this one, 9 t0 become this one. So this is the evolution of the error function diffusion profile. So we have some important consequences from the error function. So first, we have the symmetry about the midpoint. You can see this is the midpoint. So the top part of this curve, the top curve is symmetric to the bottom part of this curve. And also that we have the constant surface concentration. So the surface concentration here is constant over C over 2. It's constant. But this is also important. So this error function solution is made up of some of the Gaussian data function solutions. This is what we see here. For the integration. So those beyond x equal to 0 continue to increase with the annealing time. So those see, this is the dose. You can see the dose here. So this is the dose. C dx is the dose. So this one will increase with the time. You can see become higher and higher. So now we look at this error function, some property of error function. So this is by definition, so this is error function x. So x appears here. So when x equal to 0, x equal to infinity. So we have done this before equal to 1. Even though the derivation become like this, second derivation become like this. When x is much smaller than 1, this one equal to approach 1. So they have 0 to x 1 times du. Then this one, is very easy. You get this formula here. So complementary error function equal to 1 minus error function, so equal to x on the bottom. When the x equal to 0 equal to 1, infinity equal to 0. So when for the integration of the complementary error function is given by 1 over a square root of the pi. For the case of the x much higher than 1, so we have this formula here. So this one I'm not sure how to derive it, but now I can show you how to derive this equation here. So we want to show that the integration of the complementary area function is equal to 1 over square root of pi. So this one, by definition, complementary area function is given by u x to infinity e minus u squared du. You can see, so the integration is from u equal to x to infinity. So u is this corresponds to this shaded area. So u from x to infinity and x 0 to infinity. So we can represent the same shaded area by the second form. Now here we can see x equal to 0 to u. X is from 0 to u, right? 0 to u. The u equal to 0 to infinity. So we have the same area. So then you can see here x equal to 0 to u, x equal to 0 to u, x equal to 0 to u, u equal to 0 to infinity. So then we can integrate x first. We can do the integration of x first. But this one is very easy. So equal to u. So then we have this one. So this one, we have u du equal to du squared. So in the end, we get very easy to get 1 over square root pi. So basically, we represent this integration area. So we have this easy integration. So here we can see that. So we have a constant surface concentration. So we have constant surface concentration. So this constant surface concentration corresponds to the situation of, for example, the situation of diffusion from a gas ambient. Diffusion from gas ambient. So that means if we look at here. So the surface concentration in this pre-deposition step. So the surface concentration is constant. So the number is given by the dopant saturated at the surface. So it's given by solubility. So this one is for the doping process. So the total dose Q increases with the time, as we see before. The total dose Q increases with the time. For the drive-in, we know that the total dose is constant. It just to redistribute the dopant profile. Then the boundary condition will become, so the boundary condition will be for time equal to 0, the dopant is 0. For the time equal to t at top surface x equal to 0, the dopant is constant given by Cs. Then you can see from this one we know that this one we satisfies the fixed second law. We satisfy this equation here. So satisfy this fixed second law equation. At the same time, it also satisfies this boundary condition. It also satisfies this boundary condition. You can see here. So for this one, t equal to 0. For t equal to 0, then you see this one become infinity. So this one equal to 0. So when the x equal to 0, this one equal to 1. So we have this Cs. We have the Cs. Then this one will be the solution because this one fits the equation and also it fits the boundary condition. So then in the end, this is the dopant profile. So this is the 2 square root dt equals to 0.1 mil, 0.5 mil, and 1 micrometer. So the Cs, as we said, is limited by the solid solubility of each material into the silicon. Then the total dose. So we want to know what is the total dose. So the total dose is given by integration 0 to infinity. This formula here, dx. So we have seen this one. So integration, complementary area function integration is given by 1 over square root of pi. Then this one, we get this formula. So this is the dose. This is the dose for the pre-deposition dose. So now we look at successive diffusions. This corresponds to the case, for example. So we diffuse at a certain temperature, at temperature 1 for T1. Then we put the sample. We take the sample out. We put the sample back again at temperature 2 for the time of T2. Then what is the final profile? So the final profile depends on the total dt product. So if you look at here, you look at this one, we can see the dt always come together. So here we have dt. Here we also have dt. So here dt. So d and t, they always come together. dt always come together. So then if we know the dt, we will know the profile. So in this case, the the total dt is the sum of the individual dt. With this one, you will do the assignment to show this. But here we can make some simple argument. For example, so the profile is the Gaussian function at time t equal to t0. So this one is Gaussian. Then after further diffusion for another 3t0, the final profile is still Gaussian, which is the total t value equal to 4 times t0. So this makes sense because we have the same sample just to diffuse a longer time. So this 4t0 equals t0 plus 3t0, as you see it here. So this Gaussian solution holds only if the dt used to introduce the dopant is small compared with the final dt value for the drop-in. That means our initial delta function approximation is reasonable. But this is why I said, so this one is good. That is why I said if this one is good, if this one is very, very thin, if one is very thin, then we can approach this one as the delta function. So for when the d is the same, that means for the same temperature, the total value is d, the total time. So when the diffusion at different temperatures, so we can do some rearrangement. So equal to d1, t1, d2, t2. This one is d1, t1. You can say d1, this one is the same thing. So you can effectively think this is another time, because anyway, d and t they're always together. So now we finish the few cases that can be solved for the diffusion equation. So now we'll look at some special topic. The first one is the non-ideal and extrinsic diffusion. So we know that the fixed law is only valid for the diffusion under special conditions. For example, so when the doping is higher than Ni, then we have the electrical field. We have electrical field effect. Then this one, the Gaussian solution, what we see before, will no longer be valid. This is as we see here at the beginning, somewhere here. So far we have seen we need to be intrinsic. That means the dopant concentration should be smaller than the intrinsic concentration. But this is typical the case because at high temperature the Ni is a pretty high value. But normally the Na and Nd they satisfy. So normally this condition is satisfied. Otherwise, if this condition is not satisfied, then we have to consider this. Electrical field effect. So when we have the electrical field, so this because the field comes from the higher mobility for the electrons and holes. So obviously, electrons and holes they can move faster than the dopant atom. So this dopant atom diffuse slower than the electron and holes. For this case, we have an n-type dopant. So we have electrons. Those electrons move faster than arsenic dopant. But then we have this electrical field until equilibrium is attained. Because of the electrical field, the field slow down the electron and speed up the dopant. Then we have this equilibrium. You can see it here. So when we have the field, the dopant profile, initially we have this profile. After some time, we have this diffuse with the electrical field. So here you can see this is the dopant concentration. You see the numbers 10 to the power 20 and 10 to the power 19. They are all very high. So normally we do not have those high doping concentration. Then the previous what we talked about previously will be good. But when we have this very high dopant concentration, we need to consider this electrical field. So after diffusion, the profile becomes like this. So normally you may think, so this is the peak. The peak is here. But usually after diffusion, the peak should be still here. But here I think the top is capped. That means corresponds to this situation here. So the top we have this oxide here. The top is capped with silicon oxide. There is no after diffusion. So when there is no after diffusion, the dopant concentration here may become the peak. That's why what you see here. So the top layer here, this one becomes the peak. So not only the dopant, but also the substrate atoms, substrate dopant. So when we have this field, so the substrate dopant will also be affected. In this case, it has the p-type. So p-type is negatively charged. Then the profile become like this. So we have this movement over the substrate dopant materials. Second effect is the concentration dependent diffusion. So we see that for previously, so we have this. So we have been solving this equation here, D. So we have been solving this equation because the D is constant. So when the D is not constant, so when the D is not constant, so we need to leave the D inside. So this is what we get, as you see here. So you can see. So when the D is not constant, so we have the D. So inside this part, so we need to solve this equation here. But this one cannot be solved. It cannot be solved analytically. It has to be solved numerically. But there are a few possibilities. So when the D is constant, so we know we have this one is the Gaussian. So this is the equal to Gaussian. So when the D is not constant, for example, if D is proportional to n, the carrier concentration, it becomes this blue curve. So when the D is proportional to carrier concentration square, so we have this green curve. So this curve here, so not like this. It's not that now this one become this one. This is just the drawing of the shape rather than this one after diffusion become this one. So you can see here. So what do you see here? We have this box-like very steep doping profile. This steep doping profile is often desirable. So now we look at the dopant segregation and the effect of the thermal oxidation. So first is the dopant segregation. But this one, as we see from chapter 3 for the wafer growth, so we define segregation coefficient is given by. So when we do the thermal oxidation, so then the dopant at the inner phase, we have this segregation coefficient. It's defined as the dopant concentration of silicon over dopant concentration in the oxide part. For the chemical boron, this number is smaller than 1. You can see here. The boron substrate depletes the boron into the growing silicon oxide. So the boron, they prefer to stay in oxide. The ratio here, the number here, is given by 0.3. For the other dopant, arsenide, antimony, and phosphorus, this one roughly is 10. You can see here. The dopant concentration in the growing thermal oxide is here, like 2 times 10 to the power 17. Inside the silicon, it becomes like you can see here. This is like nearly 2 times 10 to the power 18. So it's about 10 times. Now this is the dopant segregation when we do the thermal oxidation of the wafers. Another effect is called interfacial dopant pile up during the oxidation process. So in this case, the dopant may segregate into an interface layer. So this one may be only a monolayer. So this monolayer, the dopant here, the dopant lost, they are not electrically active. They do not contribute electron and holes. But this may consume up to 50% of the dose in the shallow layer. So now we look at how to do the diffusion doping process. So you can see the process is similar to the thermal oxidation. It is also similar to the low pressure chemical vapor deposition. So we have this furnace. So actually, sometimes we can use the same rack. So some furnace we use for oxidation, some furnace we use for the LPCVD, and some of them we use for the diffusion. So you can see a similar idea. So we pass the gases, and we put the many wafers. We put many wafers vertically like a stack. So many wafers can be processed at the same time. So this is called horizontal. It's called a horizontal surface. This goes up to 80-inch wafers. So when we have bigger wafers, then we have this vertical furnace. So this is the diffusion method. The source can be a gas source, a liquid source, a solid source, or sipping on a glass. You can see here. What do you see here? The first one is the solid source in a platinum source boat. So we put the material in this platinum source boat. So we put the source material inside. Then this one is hot. Then it will be vaporized. Then it come to the wafer. Second one is the liquid source. In this case, we have the nitrogen to bubble through the liquid, then come to the wafer. The third one is the gaseous source. Here we have this dopant gas come to the wafer to dope the wafer. So afterwards, we have this burn box. So we use oxygen to burn away the material that is toxic. We burn away the toxic material, then we go to the exhaust. So now we look at the different dopant gases. So for the critical boron, it's typically this called dibarium. This one is very toxic. So exposure of 160 parts per million for 15 minutes, it will be life-threatening. Very toxic. And this one is sweet. And this phosphine is also toxic. It's also very toxic. And this one smells like a fish. So arsen, this smells like a garlic. For the silane and the dichlorosilane, this is for the polysilicon. Polysilicon deposition, we know we use the silane or dichlorosilane or maybe silicon oxide or silicon nitride. So those gases are used for the silicon nitride deposition or silicon oxide deposition. For the case of silane, this is the repulsive odor, burns in air, and explosive. For this dichlorosilane, this one is irritating odor. So you can smell it. When you smell it, you can run away. So now we look at the first one, a spin-on glass. So this one, the spin-on glass. How to do the spin-on glass doping. So in this case, when we spin coat a film, we have this precursor. So we have this precursor. This is called the Sol. I think you are familiar with this, the Soldel process. So we have this precursor in the solvent. Then we do the spin coating. In the spin coating, we got this film. So this film contains a silicon, oxygen, and a dopant. For example, it contains boron. It may contain the boron. It contains silicon X, Y, Z. It contains this one. This is a precursor. Then we do a high temperature process. We do the baking process to remove the solvent. So the film can be considered as a mixture of the silicon oxide and dopant oxide. For example, it can be arsenosilica, antimony silica, borosilica, phosphorus silica. This is the boron. This one is called a borosilica. There is also some organic. There are also some organic groups. Otherwise, because this precursor here contains some organic things. But when you do this high temperature, those organic component will be burned away, will be decomposed. But that's good for the many types of the dopant, and it's a very cheap way. You do not need any equipment. You just do the spin coating. You do the high temperature process. Then the doping will be done. And now we look at the gas doping. The first one is the boron. The chemical reaction is the boron oxide to react with the silicon to form the boron and the silicon oxide. So normally, to the dopant, for example, boron may be 10 to the power 17 per cubic centimeter. For the chemical silicon, we know that this 10 to the power 22 per cubic centimeter. So you can see the boron and silicon is very small concentration. So even though we have this equation here, there's not many silicon gets consumed by this process because the silicon is 10 to the power 22. So the idea is to form this boron oxide. So this coming. So we have the solid source is boron nitride or trimethyl borate. This trimethyl borate with oxygen to form the boron nitride. And then this boron oxide. This boron oxide will form the boron dopant. Boron, we can also use the boron nitride. The boron nitride reacts with oxygen to form the same thing. For the liquid source, the BBr, this one is liquid. For the gas source is the diboron, as we said before, with oxygen or CO2. So you can see here, so all the process, here we have oxygen here and oxygen here. So all the dopant process, we need this oxygen. We need oxygen to form this boron oxide. So the same thing is here for the phosphorus. It also this becomes the phosphorus oxide. So this one can also be a solid source. This can be a solid source, for example, phosphorus pentoxide. This one, or we can use this ammonium monophosphate, ammonium diphosphate. We can also use the liquid source, POCl3. I think this one is more popular. POCl3 to react with oxygen to form the PO5, then the PO5 reacts with silicon to form the phosphorus dopant. The gas source is the phosphine. This is also a popular one. Phosphine oxygen to form this PO5. For the arsenate, so it is possible to have the solid source, but normally we use this arsine. Arsine and ion implantation is normally used for the deposition. For antimony, it's the same thing. So we have this antimony oxide to react with silicate to form this silicon oxide and antimony dopant. So the liquid source can be antimony chloride, but usually we do ion implantation for the doping of antimony and arsenate. Okay, thank you.